So this class, we're gonna continue our discussion on the particulate matter, okay? So let's again do a quick recap of last class. So last class, we just go through some basic introductions on what is PM, right? And how it's affecting our daily life. So if there's one sentence that I want you to memorize from this class, finally, when we reviewed all the contents, so I want you guys to memorize one sentence. That's a definition of the particle. Basically, a particle is a stable cluster of molecules. Okay. So this is the one sentence that I want you to memorize. There's also one equation that I want you to memorize, but that's going to be later on. It's about the particle dynamics. Okay. So finally, when you finish the whole class, if I want you to directly write out something without checking the book or checking the class notes, those will be the 2 points that you get from this class. All right. So why is it important? It is categorized as one of the 6 criteria air pollutants. And of course, when we define it as criteria air pollutants, we think it's bad for our human health, right? But it's also affecting all aspects of our daily life. For example, through light scattering, right, affects the Earth's energy budget. Through cloud formation, because each cloud droplet, it has a particle inside, right? It's going to affect the source, sink, and evolution of the particles in the atmosphere, right? And of course, it has health effects, and it also can be used for these nano-engineered devices. So it's being applied in almost all aspects of our daily life. So last class, we didn't talk about the source of the PM. So in terms of the source or the way that the PM is generated, you can categorize them basically based on how they're being formed. Okay, so there's a top-down approach and a bottom-up approach. So the top-down approach is more straightforward, right? So basically, we're just generating particles by breaking things apart. I think we have probably have the impression that when our department or the department building, Buckler Carlton Hall, had the north part being constructed, there are a lot of particles being generated every day. So whenever we walk past by, we'll basically mask our mouths, right? We don't want to inhale any of those particles. So those particles, or those PM, are generated by breaking things apart, either by drilling or sanding, or basically breaking larger pieces of rocks into small particles, and they can suspend in the air, right? It's basically a top-down approach. So there's also a bottom-up approach. That is by basically very small molecules. So they coagulate, or they assemble with each other to form a particle. So we say that a particle is a stable cluster of molecules, right? So this is how we are forming stable clusters. And the most direct example is the combustion process. So for example, when we go camping and we do barbecue outside, we always can see black smokes being generated from the fire, right? So those are the particles that being formed from this bottom-up approach. So when we combust these fuels, it generates a lot of carbon, right? Or organic species, organic molecules. They will assemble with each other and form these larger particles. So this is another example of the bottom-up approach. So I think you guys probably heard of the Smoky Mountain, right? The Great Smoky Mountain. It's one of the national parks. So the reason why we call it Smoky Mountain is because it seems that the weather there is always so hazy above the forest, right? So there's a reason that we call it smoky, and it's not because people are camping there. It's not because people are burning woods. It is mainly because the forest, or basically all the plants, they will emit volatile organic compounds. Or VOCs. So we introduced that in our first class as well. Basically, some of the VOCs can be very toxic to human beings, but for a lot of these plants, they are benign to human, right? They're not harmful. We also mentioned that the VOC is a kind of like a precursor to form ozone, because we said ozone is a secondary gas pollutant. It can be formed by NOx, right? And it can also be formed by VOC under the solar radiation, under the photon. Right? So basically what happens is that a lot of these trees generate VOC gas molecules. And then under the solar radiation, it's going to form ozone. And then through the reaction of the VOCs, ozones, and sometimes there can be other gas species floating from some other regions. And then these gas molecules can basically assemble or collide with each other and form these tiny droplets or tiny particles. Okay, so this is basically a secondary formation of the PM. So combustion is a primary or it's a direct way. Right? So from combustion, we're generating these particles directly. So this is a primary approach. We also have the secondary approach, where the PM is not directly formed over the forest, but it's through the reactions of these gas species and basically create these hazy type of weather there, right? So this is about the source of the PM in the atmosphere. And then because the PM is very important, we also have to know how we're going to quantify the PM, right? So basically, what are the properties that we're most interested in the PM? So of course, mass concentration is very important because EPA and NAAQS, basically in that table, it tabulates the limit of the mass concentration for PM 2.5 and PM 10, right? So if I remember correctly, the PM 2.5 is 35 microgram per meter cube, and PM 10 is 150 microgram per meter cube, right? And this is for 24-hour average. So one thing that I forgot to mention is that there's a reason why PM 10 is that the limit is higher than PM 2.5, and it's quite straightforward because the 10 and 2.5, that's based on size, right? PM 10 is the mass of particles below 10 micrometers, and PM 2.5 is the mass of particles below 2.5 micrometer, right? Therefore, PM 10 always contain PM 2.5. So that's why the mass limit is also higher than PM 2.5. So therefore, we know that mass concentration is, of course, a very important parameter that we want to quantify, right? And this is more about the health to the human because people are realizing that the higher the mass concentration in general, then the more severe those respiratory symptoms will show up, right? But in terms of the cloud formation capability, let's say if a particle goes into the atmosphere and then water will condense onto the particle and form a cloud droplet, then it's not the mass that's determining this process. It's a number, right? It doesn't matter whether the particles is large or small. If it's large, it can also form this cloud droplet. So under this situation, we're interested in the number concentration, right? We're interested in the exact number of these particles. So I know that you guys don't have a background on this, but let's just do a quick guess of what are the general number concentrations of particles, okay? So the question is about how many particles are there in typical indoor environments? I gave 4 options. Okay, 5 more seconds. All right, we'll stop here. Okay, so the correct answer is the last one. It's 1,000 particle per cc. So that's in general the indoor environment. Okay, so actually this concentration is relatively low compared to a lot of other scenarios because indoors we have the HVAC system, the heating, ventilation, and air conditioning system that basically filters the air. So that will ensure us to have a cleaner environment. And because of COVID-19, I think the CDC also put out recommendations regarding which type of filter we should use to further clean our air. So we'll talk about this filtration later on in our class. But if you guys are interested, you can search for the term called MERV 13. So basically, this is a rating of the filters. Okay, so the CDC or NIOSH put out this recommendation that in general, the universities or schools, they should use a filter that's equal or better than this MERV 13 rating of the filters. Okay. Since we talk about number concentration in the indoor environment, I'll also list out the situation for outdoors. So we said the indoors is around 1,000 particle per cc, right? Centimeter cube. So for outdoors, in general, the concentration is 10 to the 4th to 10 to the 6th number per cc. Okay. It is a lot higher compared to the indoor condition, right? And basically, this is what happens when we move our instrument outside. We can see that the concentration is in between. And of course, it depends on which outdoor environment we're talking about. If we're talking about the urban area, concentration will be higher. But if we're talking about the most cleanest or the cleanest environment, for example, the Amazon basin, where people don't live there, it's full of trees, right? Full of forest. The concentration will sometimes even fall below 1,000 per cc. So it really depends on which type of outdoor environments we're talking about. And right downstream of a car engine, people actually have measured that. And that's around 10 to the 12th number per cc. Okay, so these numbers differ by orders of magnitude. So now you can see why people want to purify, why people want to remove the particles from these fossil fuel combustion processes, because they just generate too many particles, and if we directly inhale them, that's going to be harmful to our respiratory system. Okay, so in terms of concentration, we talk about the number concentration, we mentioned the mass concentration, and people are also sometimes interested in the surface area concentration, and this is mainly because regarding the toxicity of these nanoparticles. In general, it's their surface that's interacting with the cells. Let's say this is our lung, the alveolar region, right? Remember, and the lung is full of different branches, right? And then to the main duct, right? Let's say this is the endpoint of our respiratory system. Then when we talk about the interaction between the particles and the cell here, that's living by here, it's mainly the surface of the particles that decides a lot of things, right? So if they have a higher surface area, then the damage will be higher. That's why people also measure the surface area concentration. So this is basically the concentration is one aspect of property we're interested in. And another aspect is the size. This is also very important. You can see that directly from the definition of PM 2.5 or PM 10. So the 2.5 and 10 are the particle size, right? Mainly because particles with different sizes, they're going to show different health impacts, right? And specifically for the 2.5 and 10 here, they're basically micrometers. So 1 micrometer is 10 to the -6 of a meter, right? So I think if you search for PM on the EPA website, they always like to show this graph here. So basically this picture shows you in general what are the scales of these particles, right? So here it shows basically one string of the hair. So in general, the human hair really depends on different people, but in general, the human hair has a diameter of 50 to 70 micrometers, which is already quite thin. And when we talk about beach sand, the fine beach sand, actually they have a diameter of around 90 micrometers. So when we talk about PM10, that's around 1/5 of a human hair, right? Which is further smaller. And when we talk about PM 2.5, that's further a quarter of the PM10 in terms of diameter. So you can see how small the PM 2.5 can reflect or compare against the human hair. This is very small scale of the size. And later people realized that in general, the smaller the particle size, the higher the toxicity of the particles will be. So people are also right now pushing to form more standard about PM 1.0, which is particles below 1 micrometer. So this is going to be further small scale in terms of the diameter. And right now we have a lot of instruments actually can measure down to further below micrometer. So I think a few of you are in my lab, and we have the instrument that can actually measure particles from 30 nanometer to around 20 micrometer, okay? So we have a set of instruments to look at the particle concentration with different sizes. We can cover a wide range of particle size and measure their concentrations. So in this way, we can have a better understanding of how bad the air quality is, right? So this is about in general, the physical size. This is how we look at it and then directly can tell how large the particle is. So there are some other sizes as well. For example, the aerodynamic size. Aerodynamic size generally describes how fast the particle can move in the stream, right? So we know that if a particle, let's say we have two particles of the same size, but one is composed of water and one is composed of, let's say, iron, right? So we know that iron has a higher density compared to water. So in this case, it's going to move faster. It's going to move faster compared to water droplet. And because of that, the aerodynamic size of the iron particle is going to be higher. It's going to be larger compared to the water droplet. This considers the movement of the particles. And we'll also people also use the volumetric size. And this is mainly because we're basically assuming that right now particles has a spherical size, but generally, if you look at the microscopic structure of these fine particles, they have all different shapes. They can have the square shape, right, the cubic shape. For example, the sodium chloride particles, they will have a cubic shape, right, because they crystallize and have their own structure there. And for example, the combustion aerosols, they will have a lot of these branches, okay? So each of the particles, they will compose of very small, fine spherical particles, but they're all connected with each other. So under this situation, we're going to define a new diameter, which basically have the same volume of this particle, right? So we can think of it as compressing it into a sphere, right? So this new sphere, the diameter of this sphere is going to be the volumetric size of this particle here. Okay? So there are further different sizes, such as mobility size. We're not going to talk about all these different sizes in here. So what we're going to assume from now on is that all the particles or all the PM we're dealing with are spheres. Okay. So from now on, all particles are spherical. Okay, so we can make this assumption, and they may not have the the size. They may not have the equal density there, but in terms of their shape, we just assume that they are round spheres. Okay. So this is again the demonstration of the particles with different sizes. And if you're interested, you can also go through a textbook. I think it's chapter 3. They have a table there showing what are the general sizes of different PM in the air. So for example, let's say fly ash, and it's from the co-combustion. They generally have a size between 1 micrometer to around 200 or 300 micrometers. Tobacco smoke, generally smaller, right? Let's see, I'm not sure if they show bacteria or virus. So in general, the virus will have a size of somewhere here. Okay, so for example, the coronavirus we talked about, it has a diameter of 60 nanometer to 150 nanometer, which is approximately, 0.06 to 0.15 micrometer. Okay, somewhere here. Bacteria are generally larger. They're above 1 micrometer. So these are the bacteria. Okay. So here we mentioned about the particle size, and also people are interested in the particle number concentration. So how do we measure them? I mean, for example, we are the EPA experts, and we want to tell whether the air quality at certain location is good or bad. We need to bring some instruments there. So there's no way that we can collect all the particles and count how large they are, right? So we have to use some instruments there. So the most widely used instrument is called the Cascade Impact. So basically the cascade just means multiple stage. Okay, so for example, for this impactor, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It has 10 stages. Okay, so each of the stage are going to help you collect particles of a specific size. So you can think of the particle movement through the impactor as, let's say we're driving through a very narrow tunnel, right? So many of the tunnels are straight, but let's say we are driving through a bent tunnel here. So if we drive a very small car and we know how the road looks like, we can still make the maneuver to turn around, right? But if we're talking about very large truck, we have a small car and large truck. If we have a large truck, it's going to be very difficult for us to make the turn, mainly because the truck has a very large inertia. So they have a large velocity, so it's going to be very difficult for them to make the bend or make the turn. So the same works for the impactor here. So what happens is, for these impactors, generally this is the inlet, okay? And at the bottom, there's an outlet. And for the outlet, it's normally connected to a pump, okay? The pump will pull certain flow rate through the whole system. So if we just make a cross-section view of this impactor, this is how it's going to look like on the right-hand side. You have the first stage, second stage, third stage. So let's say we just have 4 stages here. So cascade impactors, they have different number of stages. So at the end, there's also a filter to collect all the escaped particles, okay? So let's say we're trying to throw particles of different sizes into this inlet here. We talk about very fine beach sand, right? So that's somewhere around 50 micrometers. Sand particle. So let's say we also throw in a little bit larger particle. Let's say this is a ping pong ball. Okay, let's say we have another larger particle. So last class I said that I like potato a lot. Let's say we also shooting potato in here. okay? So we throw in particles of different sizes, right? So similar to this driving through the tunnel thing, they first will, because of the pump, they will have certain velocity, right? So they'll have an airflow going through. And here we have a stage that's fixed at the center of the stage, right? At the center of this this single stage of the impactor, right? The airflow will have to go around this stage because the airflow is not going to directly go through, right? The stage is always solid. And because of that, the particles will also try to flow with the airflow. So for the very small particles, for example, the sand particle, it can just go with the flow, so without hitting the stage. But for the larger particles, because of their larger inertia, let's say the ping pong ball can still go through. We have the sand, we have the ping pong ball, but for the potatoes, it will inevitably just hit onto the stage, right? If the velocity is high enough, we probably can get mashed potatoes. So that's why we can basically filter out the particles, the larger particles, with the first stage here. And then these remaining particles will go through the second stage. And you see this, and there are some differences between the first stage and the second stage. So first thing, it's the inlet diameter. Okay, you can see that the diameter gets shorter. If the diameter gets shorter, then the flow velocity will be larger through this narrow inlet here. So the higher flow velocity will give particle a higher inertia, right? So basically we're accelerating the remaining particles. And if they have a higher inertia, so we're basically enhancing their inertia. So this time maybe the ping pong ball will get collected. And at the same time, you can see that the distance between the inlet and the stage also becomes shorter. So it's further easier for us to collect particles with the intermediate size, right? So in this time, particles of the intermediate size can get collected, and while the sand particles can go through and then go to the third stage. So in the third stage, we further narrow the inlet diameter and shorten the distance between the inlet and the stage, right? This time we can collect the sand particles. So finally, let's say after 1 hour or 1 day of the sampling, what we'll do is we'll take out the stage and then do the measurement, right? We can measure the mass of the particles on each of the stage. Let's say this is M1, M2, M3, M4, right? And because finally what we want to get is the mass concentration, which should be microgram per meter cube. We always need to divide this mass by a volume. So the volume is just going to be the airflow that's would pull through over the entire sampling period. It can be 1 hour, it can be 1 day, because for the pump, it has a flow rate that's tabulated, right? The pump, let's say it samples airflow at a flow rate of 1 liter per minute, right? So if we sample for 1 hour, then that's going to be 60 liters, right? So we can just divide this mass by the volume to get what is the mass concentration of particles that's collected on here, right? And generally for these impactors, they have to be operated at fixed flow rates and also fixed temperature, right? Because of that, basically for each stage, we can calculate what is the size of the particle that will get collected. So for example, the first stage will collect particles that are above 100 micrometer. Second stage, let's say 10 micrometer. Third stage, 2.5 micrometer. Fourth stage, 1 micrometer. Okay. So what this does is that in the first stage, it's going to collect particles larger than 100 micrometer. Second stage, larger than 10. Third stage, larger than 2.5. Fourth stage, larger than 1 micrometer. And because of that, let's say if we want to know PM 2.5. So PM 2.5 are particles below 2.5 micrometer. So we can just measure particles that are on this stage, right? Because the stage here collect particles larger than 2.5, and those particles that can travel through this stage are the particles below 2.5 micrometer. So we can measure the mass of the particles on this stage to get what is PM 2.5. And similarly, if we're interested in PM 10, we're going to measure the mass of particles on these stages, right? Because we want to measure, basically know the entire mass of particles below 10. We have to measure or combine the mass collected in these few different stages. So basically, based on this principle, we can provide what is the mass concentration of particles in different size ranges. So any questions until now? I hope this is clear enough, because we're going to use this concept quite a lot in this class. I just want to show that this is how we're going to mainly generally measure the size distribution of particles. Does that make sense? Good. Okay. So you will also have more practice with this problem here. Okay. So basically, this is how we measure particles with different sizes. And what we can finally do is we can make a plot that looks like this. So on the x-axis is the particle size, and on the y-axis is the mass of the particles. So what we can plot is we can plot out what is the mass of particles in between 10 and 100 micrometer for this impactor here, right? And we can plot out what is the mass of particles in between 2.5 and 10, and also 1 and 2.5. Right, for our impactor here, let's say this is a 4-stage impactor, right? Because this stage collects particles above 1 micrometer, but are below 2.5 micrometer. And this stage collects particles above 2.5, but are below 10 micrometer. Okay. So basically, we can make this plot here to show how the size distribution looks like. And of course, we're just talking about a 4-stage impactor. But in general, people will use more than 4 stages, maybe 10, or sometimes they can even use 20 or 30 stages, right? So what that means is that we're going to get a size distribution that looks a lot denser. Let's say this is the particle size, mass. We can get something let's say something looks like this. All right, we have different stages, and here this is what this size distribution or this mass concentration here will come from the stage 2, right? Mainly because the first stage collects everything above certain size. It's only the second stage that we can get within a size range. The second stage is 10 to 100, right? So here, this is a size range here. This is going to be stage 2, 3, 4, 5, 6, so on and so forth. Okay. So we call this type of distribution as the size distribution, because it tells you what is the mass concentration of particles with different sizes. We're trying to specify the concentration to the respect of particle size. Okay. So now we may have a question. So is this, let's say this is what we measure from outside, right? Outside the building. But when we look at the size distribution, this is not going to be the actual size distribution, right? So one question you may have is, let's say here is 1, 2, 3, 4. This is micrometer. Okay, it's 0.5. So I'm not showing them in a linear scale. I'm just making up these numbers here. So let's say for this size range between 1 and 2 micrometer. So what about the concentration of particles, let's say, have a size of 1.2 micrometer and has a size of 1.8 micrometer? So are their concentration the same? Because based on this bar plot here, it seems that they have the same concentration. But in the actual situation, they will not be the same, right? It's not saying that all the particles within this size range has the same concentration. So here we're just representing the size distribution with a discrete form, but the actual size distribution should always be a continuous curve there, right? So you should have a form that looks like this. So this is how a continuous size distribution looks like. So particles of a unique size will have a unique concentration, all right? And this is also in general how the size distribution looks like in the outside air. So when we do the measurement, let's say for the raw ambient air, we're not going to show something that looks like very narrow peak and very narrow peak. In general, they're just going to show a broad peak. And at certain size, they're going to have a highest concentration, but normally they're quite broad. Okay. So once we know how the size distribution look like, of course, people always want to simplify things, right? In general, we don't want to do this measurement whenever we go to somewhere. So that's why people also want to quantify these size distributions with some mathematical equations, right? So by first looking at this curve, if we want to show it with a mathematical equation, maybe the first type of expression we can think about is a Gaussian distribution or normal distribution, right? Normal distribution is something that has the highest concentration in the middle, right? And then has lower concentration or lower values at the two tails. So we'll first try to, people first try to describe these size distributions with the Gaussian distribution. So that's why they come up with this equation, M total sigma square root of 2 pi. Okay. So this is the equation that people first think about. So basically, they will try to fit this size distribution with a Gaussian distribution. And here, the M total is just the total mass concentration of the particles. Because what we want to make sure is that basically the integrated area, if we do the integration, then the integral of this equation have to be equal to the total mass concentration. So that's why it's sitting here. So sigma is the standard deviation of the size. dp bar is the mean size of all the particles. But then people realize that there are some problems. So first, basically for the outside air, it generally looks something like this. So we have a very steep uphill part, and then a very tapered or very long tail for the size distribution. But when we're trying to fit it, let's say with a normal distribution, we know normal distribution and Gaussian distribution, they are symmetric, right? They cannot show this very long tail here. So this is problem one. Normal distribution cannot show the tail. And secondly, there is another critical issue actually for this Gaussian distribution is that when dp is smaller than 0, let's say if we try to plug in a value that dp equal to -1 micrometer, we can still get a positive mass concentration. And this is very problematic, right? Because the integral of this whole size distribution doesn't care whether the size is positive or negative. But it seems that by using this Gaussian distribution, it also accounts for particles that are smaller with a negative diameter. This doesn't make any sense, okay? So that's why people try to modify this equation. So why don't we just put a constraint on the particle size that we put in as a parameter here? So what they do is they come up with a distribution that's called the log normal distribution. So instead of showing the particle size in the linear scale, they decided to show the particle size in the log normal scale. Okay. So by meaning log normal, I mean the spacing between one order of magnitude is going to be the same. Okay. So in this way, we can show the tail more efficiently, because we know that there's a long tail, right? Meaning a long tail, we mean particles can have a very large size at the end, right? So by shrinking, basically, by showing that in the log normal scale, we're shrinking the x-axis. So they're going to look more symmetric in this way. And at the same time, if we look at the equation describing the log normal distribution, it has an equation of dp log sigma g. So here I just write log, and I meant log 10 in here, okay? Exponential minus log dp minus log dpg. Okay, so this is the revised equation that people use to basically model the ambient aerosol size distribution or ambient PM size distribution. So you can see that a smart part for this equation is that we use this log to constrain the range of the dp, because we know that dp cannot be negative if we try to plug in this natural log term, right? So by this way, we naturally constrain that all the dp have to be larger than 0. Okay, and there are some minor differences between these two equations, right? For the normal distribution, log normal distribution. So if you compare, we have a dp in the denominator. Well, we don't have one in here, right? And also in here, we directly have the sigma, but here we have the log sigma g. And this is mainly because finally, we still want to make sure that the integral of this log normal distribution have the value of m total, right? We always want to make sure that the area below the curve is the total mass concentration. So that's where these terms come out. So if you're interested, you can also do the integral. I think in calculus, you guys already went through this process. To do basically, you can integrate this term, and you can find out that the solution is just the m total showing here. Okay. So you don't have to memorize these equations, but this is just trying to show that how people are trying to use some mathematical expressions to show the how the size looks like, how there's a way to improve the representation of these size distributions. And we're indeed going to show a lot of size distributions that are in the log scale, right? We're not going to show that in the linear scale, right? So, so once we have the size distribution, and people also get more creative. This is just showing you what is the concentration at a specific size. And people are also interested in a term called cumulative size distribution. So what happens is this is trying to get or plot out the cumulative fraction cumulative fraction of particles below certain size. Okay, so let's plot out our log normal size distribution again. dp 0.01, 0.1, 1, 10, 100. We have m here. Okay, so this is our log normal size distribution. So the cumulative fraction is just, so we're just trying to basically get answer the question. Let's say the cumulative fraction of particles below 1 micrometer is just the entire mass that are below 1 micrometer divided by the total mass. Okay, divided by the total mass. So based on this relationship, we know that the cumulative fraction of this at this particle size of 1 micrometer, so that's going to be 50%, right? Because 1 micrometer is at the center of this log normal distribution. Okay, so that's going to be 50%. Then what about, let's say, dp equal to 1,000? Then at 1,000 micrometer, what's going to be the cumulative fraction? That's at the end, right? So that's going to be somewhere around 1. Okay. And let's say, what about 0.001? That's going to be somewhere around 0, right? So basically, the cumulative size distribution is just, we're trying to calculate what are the fraction of total particles below certain size. So now we can also try to plot out all the other data points. So because the fraction of particles that are around 1 micrometer are pretty high, so we're going to see a steep increase of the cumulative fraction. And then the increase are going to be slower, right? It's going to be something like this. 0.001, 0.01, 0.1, 10, 100, 1,000. Okay, so we call this representation as the cumulative size distribution. So instead of showing the concentration at a specific size, we're showing the total concentration of particles that are below certain sizes, right? So let's say we, instead of having a central size of 1 micrometer, let's say we have another size distribution that looks like this. So the center size is around 0.01. Then we know that the 50% will move to here, right? And then because of that, the cumulative size distribution will look like something like this, right? This is our new size distribution. And let's say we have a very narrow size distribution. So instead of a broader one, we have a very narrow one. So then, because of that, the increase of this cumulative size distribution will become more steep, right? It's going to be something like this. All right. So people are going to use different ways to represent their size distributions. And next class, we're going to basically show a new plot where people can directly use to show whether a size distribution is log normal or not. So basically on this plot, people also call this a semi-log plot. If we plot out all the measurement data in here, if they just show as a straight line, then we can directly tell that's a log normal size distribution, okay? So that's all for the content of this class. Just let me know if you have any questions. I know that we have quite a lot of derivations in this class, all right? Thank you.